This video covers another form of constituency parsing called Earley parsing. I'll introduce the intuition behind Earley parsing, followed by the algorithm itself. Then I'll walk through a case example to show how we could use Earley parsing to parse a short sentence. Earley parsing is another dynamic programming approach to constituency parsing. Unlike CKY, which is a bottom-up approach, Earley parsing is a top-down approach. It's more efficient than CKY because it allows you to fill a table in a single sweep rather than looping back around at the same level like we needed to do with CKY to check to see if any more constituents were matched. The entries in an Earley parsing table can contain three types of information: a subtree that corresponds to a single production rule, information about how much progress has been made in completing that subtree, and the position of that subtree with respect to the entire input sentence. Entries containing that information are usually referred to as states, and those states include structures that are referred to in Earley parsing as dotted rules. And basically, a dotted rule just uses a dot to indicate progress towards completing a specific production rule. A state's position is also indicated with respect to the input as a whole, so there will be both a start index and an end index. These indices might be the same if the state is only concerned with an individual word, or the state might span the entire input if it's representing a complete parse of the input. Some examples of what those states might look like are shown here. In the first case, we're saying that a top-down prediction for the start symbol is a verb phrase. The indices, 0 and 0, mean that the constituent predicted by this state should begin at the start of the input string, and the dot currently lies at the start of the input as well, rather than within it. So the next word we'll be trying to match is book. In the second case, we're saying that a top-down prediction for a noun phrase is a determiner followed by a nominal. The indices, 1 and 2, indicate that the constituent predicted by this state should begin after the first word, and the dot currently lies after the second word in the input. So the next word we'll be trying to match is flight, and we'll be looking for a nominal. In the third case, we're saying that a top-down prediction for a verb phrase is a verb followed by a noun phrase. The indices, 0 and 3, indicate that the constituent predicted by this state should begin at the start of the string, and the dot currently lies at the end of the string. It looks like the dot in the production rule is also at the end of the rule, so this rule has been successfully matched. This means that we've discovered a verb phrase subtree that spans the entire input phrase. An Earley parser iteratively moves through the possible states from start to finish, and at each state, one of three operators is applied depending on the current status. These operators are the predictor, the scanner, and the completer, and I'll describe each of them in more detail in the next few slides. Operators can add new states to the chart, but no states are ever removed, and the algorithm never backtracks. If we are able to complete a start state, that is, move the dot to the end of the production rule for a start state, then we have a successful parse. The predictor's job is to find new productions that could be generated. The predictor can be applied to any state that has a non-terminal constituent immediately to the right of its dot, and the new states added by the predictor are added to the same chart entry as the generating state, and they should also begin and end at the same points as the generating state. So, for example, a production rule with a dot followed by a verb phrase with a non-terminal constituent could have the predictor operation applied to it and result in a bunch of new production rules for verb phrases added to the table. If the dot followed the verb phrase in that same statement, though, the predictor operation could not be applied. The scanner operator can be applied when there is a non-terminal non-constituent to the right of the dot. In other words, a part-of-speech category. This operator looks at the current input and adds a state that corresponds to that input word itself to the table. For example, if the category verb is to the right of a dot, and verb is a part-of-speech category, then we'll check to see if our current input word matches a verb. If it does, we'll add a state indicating that to the table with the dot to the right of the word, since we already matched it. Finally, the completer operator can be applied to a state when the dot is all the way at the right end of the production rule. When this is the case, it means that the parser has completed a subtree corresponding to the production rule. This means that we need to go back and find the other states that we're searching for that subtree and create new states that are copies but have their dots advanced accordingly. For example, the completer might be able to complete the state specified when it encounters this state. We can walk through an early parsing example now to see how this works in more concrete terms. So let's start out at chart entry 0, so the beginning of our input string, book that flight. We have some part-of-speech categories and some production rules. We'll go ahead and begin at the start state. Gamma generates a sentence with the dot before the sentence. We'll check our production rules and see that we can predict that a sentence generates a noun phrase followed by a verb phrase, and a sentence also generates a verb phrase. From those states, S1 and S2, we can also predict that a noun phrase generates a determiner followed by a nominal, a verb phrase generates a verb, and a verb phrase generates a verb followed by a noun phrase. We can't add any more states because the dots for states 3 through 5 have part-of-speech labels to the right of them. However, since they have part-of-speech tags to the right of them, that means we can apply the scanner operation to states 3 through 5 and correspondingly move ahead in our input. The next word in our input is book, and we see that it can indeed be generated by a verb, although not by a determiner. So we'll add a state 6 where we'll indicate that a verb generates the word book, and we'll move the dot after the word book to indicate that we've already seen that word now. Now, when we process state 6, we can't use the predictor or the scanner operator because the dot is all the way at the end of the input. So we'll use the completer operator. We see that having a complete verb entry can lead to having a complete verb phrase entry, so we'll go ahead and add that. It'll also allow us to move forward in the production rule where a verb phrase generates a verb followed by a noun phrase, so we'll add an updated state corresponding to that rule as well. Finally, having a completed verb phrase in state 7 allows us to complete state 2, so we'll add a completed version of that state to the table as well. So now we're done processing state 8, and we have a non-terminal constituent to the right of our dot, so we can go ahead and apply the predictor rule here. We see that a noun phrase can generate a determiner followed by a nominal, so we'll add that as state 10. Finally, although we have a completion of the sentence subtree in state 9, we can't actually call this a successful parse of the entire input because we haven't made it through the entire input yet, as we can see by our start and end indicators. Instead, it's a successful parse of the single word sentence book, which isn't what we're looking for here. So we'll move on, and when we process state 10, we see that we have a part-of-speech tag to the right of the dot, so we can apply our scanner operation. We'll go ahead and do that, and we see that the next word in our input is a determiner, which matches what we're looking for. So we'll add a state indicating that a determiner generates that to the table. We'll also advance the dot forward in our input string. Then, we can take this new information in state 11 and apply the completer operation to move the noun phrase production rule forward. We can't use that information to advance any other existing subtrees, so we'll move on to processing state 12. We see that we have a non-terminal constituent to the right of the dot, so we apply the predictor and find that a nominal generates a noun, so we add that state. We move on to processing state 13, and we see that a part-of-speech tag is to the right of the dot, so we apply the scanner and see that the next word in our input, flight, matches a noun, so we add that info to the table and move the dot forward in our input string. We process state 14, and find that we can apply the completer operation to complete state 13, so we go ahead and add an updated version of that with the dot to the right of noun. We process the newly added state 15 and find that we can apply the completer operation to complete state 12, so we'll add an updated version of that as state 16. Then we'll process state 16 and find that we can apply the completer operation to complete state 8, so we'll add an updated version of that as state 17. We'll process state 17 and find that we can apply the completer operation to complete state 2, so we'll add an updated version of that as state 18. And finally, we process state 18, and we find that this time we can apply the completer operation to the entire input string, completing state 0, because this completion spans the entire input string. So we have a successful parse with the states you see here all contributing to it. Now, just like we saw with CKY, what you just saw functioned as a recognizer. It let us know whether a successful parse existed for the input string, but didn't tell us what that parse actually was. If we want to retrieve the actual parse trees produced by the Earley parser, we need the completer operator to also add back pointers to indicate where the completed operations came from. Then, once we encounter a completed sentence node in the chart, we can just follow those pointers backwards to retrieve the parse. We could visualize that just like you see here. We can see that we reached state 18 by applying a completer to state 17, which we reached by applying completers to states 6 and 16. We reached state 6 through a scanner, and state 16 through a completer applied to states 11 and 15. We reached state 11 through a scanner, and state 15 through a completer applied to state 14. Finally, we reached state 14 through a scanner. We could also use this information to fill in a hierarchical parse tree, beginning at the sentence node and branching downwards, just like you see here.